right, thanks everybody, and thanks for having me. My name is Pengyu Hou. I'm a software engineer at the machine learning infra team at Airbnb. Today, we're going to talk about Chronon, Airbnb's open source feature engineering framework. Here's the agenda for today. We will first talk about what is the necessity for Chronon and what it is. Then I'll introduce the concept of point-in-time correctness, and how things were done before in Chronon. Then we will talk about the high-level architecture of the Chronon, and I'll walk you through a few real-world examples. Lastly, I'll wrap up the presentation with some takeaways and our call to actions. All right, let's dive into it. First one is actually, why do we need Chronon? So what are some common challenges before a feature platform for the machine learning engineer practitioners? Firstly, we observed that feature definitions can be scattered all over the places. So this way, it actually can lead to poor interpretability and difficulties with debugging processes. And also due to the scattered configs, AI ML models suffers from the online-offline inconsistency problems. And some of the slow backfills, it can affect the overall iteration speed of the model. Backfill could be arguably the most time-consuming process during the overall machine learning workflow. And we also observed across the orgs that the AI ML practitioners have to write similar glue code to manage the data pipelines, and it will have lots of duplicate work across different orgs. So Chronon is here to address those challenges. So what is a Chronon? Chronon is an open source platform enabling machine learning practitioners to efficiently develop, deploy, manage, and monitor machine learning data pipelines. Let's take a look at this spectrum of machine learning applications. On the left side of the spectrum, those are mostly unstructured data, for example, image classifications or natural language processing models. On the right side, we have structured data. Those are maybe credit scores, personalizations, and recommendation engines. On the left side of the spectrum, usually those features are available all at once. It's either a full sentence or just the entire image. The feature engineering work is relatively smaller because you just need to do, for natural language processing models, you just need to do something like removing the standing words, tokenizations. For pictures, you may just do some transformations on the pixels. However, on the right side of the spectrum, those data usually arrives steadily as the user interacts with the platform. And the features has to be extracted from multiple event streams. For example, logins, clicks, and page views. It requires very iterative manual feature engineering processes. So Chronon is to simplify the process for this step. Also, with the recent popularity of the large language models, we are also working on unifying the unstructured data and the structured data for the AI models. I also want to share our journey to open source. So the project initially started back in 2017 at Airbnb. We actually iterated over 4 internal versions. And in 2022, we partnered with Stripe for beta, closed beta. Now Chronon is fully adopted within Stripe, and they are also in this summit. They will present Shepherd at 10:10 PST. Please also join them. And in April 2024, we announced open source, and the Stripe is the co-maintainer of the project. Now, let me introduce the concept of point-in-time correct. We have this chart. For the x-axis, we have the time. For the y-axis, we have feature 1, feature 2, and the predictions and the labels. So if you want to compute the features for feature one and feature two. Let's say it's a simple operation of sum. So at the prediction of P1, we should only include the raw events that are prior to the prediction of time P1. So as it shows in this chart, we should only include all the blue boxes from the left side of the prediction P1. So for feature one, we should sum up 0 plus 5 plus 7. That gives us 12. For feature two, it's 3. We should not include anything that are after that prediction time. It will cause the data leakage for the machine learning models. Let's take another example. If we want to predict P2, and this time we have to update our feature values. For F1, this time we just need to add 4 to it, so it gives us 16. For feature 2, we sum up 3 and 2, it gives us 5. And similarly, we should not include anything that are after prediction time of P2. So why is point-in-time correctness important? What are some common symptoms? So it's usually the model will perform really well in the local, but it performs poorly in the production. It is because the fact that in real-world applications, the model could not foresee the event that will happen in the future. Point-in-time correct matters, especially for time series and real-world events. Let's have a quick example. So let's say we're working on a house prediction model. Those the feature can be based on rooms, locations, size, age, etc. But we should not use the features like offers or offers received or buyer's info, because at the time of the prediction, those information we don't know yet. The number of the offers at for a house might not receive until the deal is settled. So we should not use those features from the future to predict the models. Next, I'll talk about two common approaches. What was the life before Chronon? First one, let's call it replicate offline to online. So let's say the AI machine learning practitioners, they want to start to train a new model. They will start with a SQL query to generate the training data from their data warehouse. When the model looks good in local after several iterations, now they are working on productionizing the model. At this stage, usually they will have to translate their SQL query logic to another programming language. For example, if you're using Java for your service, it will be Java. If you're using Python or any other programming language, you have to replicate these queries to your production service. So this will actually cause the multiple feature definitions scattered in multiple places. And when you translate usually those two things cannot be the exact same. So it will also lead to inconsistency problems. It will slow down the overall performance. Next approach is log and wait. Let's say we want to log a new feature. This time we will have to make code changes in the production, deploy it, and wait. But for this approach, the features are always consistent. But every time we will have to go through the code change, deployment, and wait process. If we are working on some seasonality features, then we will have to wait multiple months to collect enough features to train a model. This will affect the overall iteration speed a lot. Now let's talk about how can Chronon address those consistency problems without waiting for months. So the first is the Chronon way. We will have a single Python config file for both online and offline. and it's using the same Scala computation engine for both environments. And the Chronon will also take care of the infra orchestration work. So the AI ML practitioners can just focus on their core modeling problems. Let's talk about the high-level architecture of a Chronon. So in the left side of the green boxes, we have the feature definitions and aggregation library. On the upper side, we have the offline. The data will the training data will be written to the data warehouse. On the lower side, we have the serving path. So for both online and offline, it's actually using the same feature definition and the same aggregation library. So this guarantees the consistency across two systems. And it simplifies lots of the work for the AI ML practitioners. And for our online serving pipeline, the project is based on a Lambda architecture. Given the time constraint, I will not dive deep into that. Let's continue to some real-world examples. So this is the feature definition for goodbye. The syntax maybe sounds familiar to SQL syntaxes, but it's slightly different. Let's take a look at this example. The source, usually we can define it with some Hive tables or some real-time data sources. The keys here is the aggregation key. And next, we can define a list of aggregations. For the same input column, we can actually simplify the aggregation definition process by giving multiple windows to the same operation. So for this example, we are operating a sum, and the windows are 7 days, 14 days, a month, and a year. So the windowed operations are supported natively in Chronon. And right now we are supporting, I think, 15 operations, and those operations can be easily extended. Next, I will talk about the join. Join is used to answer this question. So what is the aggregation statistics for a certain key from time A to a certain timestamp? The aggregation statistic for a key from time A, those were defined in the group by already. And for the join, we just need to provide a left source. That will be the reference time for these features. Some of the challenges we have to solve for this join is we have to optimize the backfill algorithm to handle data skews. And if your model does not require point in time correct, midnight accuracy can be much faster. I want to also share a quick fun fact. One of our users actually achieved with 250 lines of code to define 1,000 features. That's translated to one line of code to 4 features, which is definitely amazing. Next, I want to talk about 2 new functionalities that are widely adopted within Airbnb. First one is derivations. Let's say we want to compute acceptance ratio, that we will use the accept sum to divide it request sum. The accept sum and the request sum can be easily computed from the joins or goodbyes. But if you want to compute the acceptance ratio, then usually we will have, without derivations, the user will have to write this logic in the service. Some of the challenges for those new functionalities are we have to make sure the APIs are uniform for both online and offline, and also to guarantee a low latency online serving path. So on the right side, we have an example just for the syntax. We have on the line 6, we have a derivation definition. On the line 7, we have a name for that derivation. For the line 8, we have the expression. It's accept underscore sum divided request underscore sum. And for all the expressions in derivations, they will support the Spark SQL syntax. Now let's take a look at the real-time chaining features. let's say we want to compute the average price of ice creams a user viewed in the last 14 days. This requires transformations and the aggregations along with some denormalizations. It shares the same challenges with the derivations. For example, we need to guarantee the online and offline consistency, and we also to make sure we have a low latency serving. On the right side, we have the example of how to calculate this features. On the line 3, we have the source, and I didn't include the join source here. It's basically just the join between the, for example, the ice cream ID with the ice cream price. Then we have the aggregation key is actually over users. Next, we will create the aggregation. This aggregation, this time the operation is the last K, and then we will say we will collect the last 100 user viewed ice cream price. And the window is 14 days. So after the aggregations, we can write the derivations. This example could be a little complicated, but it's also to showcase the complexity that the derivations can handle. So to calculate the average price for the last 14 days, then we can write a function to accumulate for the past 14 days for the total ice cream price and divided by the total size. Then we get the average price of ice creams a user viewed in the last 14 days. All right, let's talk about the key takeaways. So first one is Chronon is actually a declarative feature engineering framework. It handles both for both online and offline features. We use a Lambda architecture to achieve online-offline consistency and low latency serving. Windowed operations are supported natively in Chronon. And right now we have 15 operations, and it can be extended very easily. And for those operations, we sometimes we will leverage some of the sketch algorithms to address the scalability problems. And yeah. Last is our call to actions. Because now we're open source, you can see our repo at the github.com/Airbnb/Chronon. Here is the Kickstarter. You can report issues or ideas to our Git issues. We also have a public Discord channel for users to discuss problems. Now we're using a Slack, but the link is in the Discord channel. You can join and find it. I have a few additional resources. The first two is Airbnb's blog post. The third one is actually from Stripe, how they adopted Chronon to implement Shepherd. And yeah, last two are just some code repo and some introduction. Thank you. And yeah, thank you for having me. And any questions?